Hi. So my name is Catherine Lucero. I'm with the Bureau of Reclamation, and this is a paper that we did with the University of South Florida and the University of Florida. So the primary author, Haizu, and Danushika, and Abla Zayed, who's also here. So I'll do the introduction and kind of talk about the laboratory testing that went into this, and then Kyle will talk a little bit more about the modeling and some simulations that he did for temperature rise. So as we know, cement hydration is an exothermic chemical reaction that, along with relatively low thermal conductivity and low rate of heat dissipation, causes concrete members to become really hot, and that can cause thermal stresses if there's differences between the outside and the inside of the concrete. That could lead to early age thermal cracking. And so there's lots of different methods you can use to mitigate this risk of cracking. One of them is using supplementary cementitious materials. So you'll commonly see high volumes of fly ash or slag to reduce the concrete temperature rise and increase resistance to that thermal cracking. So the temperature rise of concrete mixtures containing different slag composition is not well studied. So this research was to establish the effects of the chemical or physical differences in slags on heat generation. So this is important because there's a lot of construction out there that is considered mass concrete. It's reinforced structural mass concrete, so it's like a heavily reinforced section, something like a drilled pier, large wall, large columns. So this is mass concrete, not in the traditional sense with like large aggregate and low cement contents. These usually have higher cementitious contents. And so the temperatures can get really high, up to, about 195 degrees, depending on the starting temperature and the mix design. So the research significance to this is the study investigated the adiabatic temperature rise of several different cement slag combinations. We also varied the cement types, so we looked at C150 cement and a C595 1L cement. And this findings of the study will supplement the current mass concrete structure specifications by implementing some of this provided data in the design of thermal control plans for slag blended concretes. And then this will ultimately lead to minimizing the high temperature rise issues experienced in the fields and minimizing the potential for thermal cracking. So our experimental approach was first like material selection. We really wanted to make sure we were getting a wide range of different slags, different chemical compositions, and then the adiabatic temperature rise test to determine hydration parameters, and then isothermal calorimetry to determine the activation energy for these different blends, and then finally the sensitivity analysis, varying the placement temperatures and varying member sizes and seeing how these different slag compositions will vary the ultimate temperature rise in the field. So the slags were selected for the alumina content and also the fineness. So as you can see, we had 5 different slags, and they varied from about 8% alumina up to 17% alumina content. There was one slag that had a reasonably high alumina content, but also a low magnesia content, and wanted to see the influence of that as well in the early age hydration. We also varied the fineness of the slags. So there's S10C and S10F. So those are both about 10% alumina, but one was coarser and one was finer. And then we also have the type 1-2 moderate heat cement and a type 1L cement with about 10% limestone. So again, just showing the phase compositions, and this also shows the blade fineness differences between the slags. So the coarse and the fine. So in the lab, we first started with the adiabatic temperature rise testing, and that was done at the Bureau of Reclamation. And so we did 10 mixtures with the 2 different cements and the 5 slags. They were all 60% replacement by mass. So all the concrete mixtures were pretty much the same. They all had 665 pounds per cubic yard of total cementitious, and then if they did have slag, they had 60% slag. And the water to cement ratio, water to cementitious materials ratio was fixed at 0.404, and also the water reducing admixture was fixed throughout this testing program. So we didn't try to do any adjustments to get a target slump, just all the same. So we pre-cooled the materials to about 50 degrees so that they would have a placement temperature of around 60 degrees, their fresh concrete temperature. So we did reach that target. The target temperatures were usually around 59 degrees to 62 degrees starting temperature. So this is a USBR test method, USBR 4911, which is the procedure for a temperature rise of concrete. And so basically we mix that sample, about 4.62 cubic feet of concrete, and fill a steel can. And then we have two wells that are embedded in there that temperature probes will later go in there. That can is sealed, and then a tight-fitting sleeve of insulation is placed around the can and is moved to the calorimeter chambers within about 30 minutes from time of contact with water and mixing to the start of data collection. And then two platinum RTD probes are at the center of the sample. So these this is a picture of the chambers. So we have 6 chambers, and they all have a range of negative 20 degrees Fahrenheit to 180 degrees Fahrenheit. And so the room is, to perform the adiabatic calorimetry, the room is set to the sample temperature, whatever's read from those RTD probes. The chamber will match that temperature so that there's no heat loss to the environment. And then records the room temperature and sample temperature every 5 minutes. Okay, there we go. Just wait a second. Okay, sorry about that. So here are the results. So this shows the temperature rise curve. So this isn't the absolute temperature, just the difference between the measured temperature and then the placement temperature for the first 7 days of after placement. So on the left, we have the C150 cement mixtures with the slags, and then on the right we have the 1L cement mixtures with the slags. So immediately you can see the difference between the type 1-2 cement and the type 1L cement. There's a lower rate of temperature rise within the first 7 days, so that's kind of advantageous, and you can it's kind of intuitive. There's a lower clinker factor with the blended limestone in there. But then you could also see the differences between the wide differences, the 7 days temperature rise with the varying slags. So there's actually about 8 degrees between the different types of, or the different compositions of the slag. So let's see here. Sorry, it shows up different. Sorry, they're not dotted on the presentation. But so the lowest alumina content is the light blue line, and so that's the lowest temperature rise in seven days. And then the highest is the highest alumina content. So that was kind of as expected. And you can see in the 1L cement blends, there's even a greater difference, like a lower rate of temperature rise with the slag blend. So it's kind of like a synergistic effect that you can get a lower rate of temperature rise, which is advantageous again for in the field for controlling the risk of thermal cracking. So we also determined the activation energy of these different systems using isothermal calorimetry at 3 different temperatures, and that was also used to determine the hydration parameters. So the adiabatic temperature rise data was fit to this equation, so you can see we determined let's see here, beta and tau, which had a linear relationship with the alumina content in the slag and also the magnesia to alumina ratio of the slag. So increasing the alumina content, you'll see a steeper slope factor in that third graph right there, and that's true for both the 1L cement and the 1-2 cement systems. And also the rate of temperature rise as measured by the adiabatic temperature rise testing in those first 2 plots. We also see that same trend. Increasing the alumina content will increase that rate of temperature rise. Okay, so I think Kyle's going to talk about some of the simulations.
All right, thank you, Catherine. So for the adiabatic temperature rise, we saw that it had a decrease in the rate of hydration, but overall you were seeing pretty similar adiabatic temperature rises at 7 days or beyond. And so there was a concern that some people might misinterpret what our data was saying, that slag really can be beneficial for the adiabatic temperature rise and for controlling heat in mass concrete members, because they would just look at and see the overall temperature rise that could actually be higher with our slag cements than with Portland cements if you look at it at 7 or 28 days. So what we did was we did some simulations of structural mass concrete members and looked at Jacksonville, Florida. This project was sponsored by the Florida Department of Transportation. So we were looking at Florida structures for this. So we looked at basically varying the size of steel columns, or varying the size of square columns in the summer and in the winter for Jacksonville, Florida, for these case studies, to see what the benefits of the slag are for your member. And as you can see, as the square column size gets smaller, your benefits go up. You end up with a, let's see, find that pointer here. Your benefits are a lot greater with the smaller members. As your member size gets bigger, then the adiabatic temperature rise that you have at later ages starts to hurt you a little bit, but you still have a big benefit from the use of slag. So this is for instance, our 8% alumina slag, 14 and 18% alumina slag. The benefits, you can see that the type of slag really makes a big difference in the maximum temperature rise that you have for these members, and so does the size. But overall, they reduce the temperature rise. So that's for our December placement, so lower fresh temperatures. If we look at the maximum temperature difference, you also see that same benefit. You reduce the maximum temperature, you're going to reduce the temperature difference and the risk of thermal cracking. Okay, so if we look at the summer, the benefits there are still very apparent. The type of slag that you choose definitely has an impact, and again, as your member size goes up, the benefits are still there. They're just a little bit more reduced, and so you have to take into account not just the materials, but also the member size, the construction, the time of the year that you're doing this when you're considering this in your thermal control plan. Part of the reason this study was done is in the state of Florida, we were getting slags in from places these are coming mostly in from Asia, where they do have these high alumina contents, and they were seeing a lot higher temperatures measured in their mass concrete members than they were in the past, and so they wanted to know why this was happening and how these affected it. So overall, all of the slags had a lot of benefit on the temperature rise, but you have to plan your materials with your construction accordingly. Here's the maximum temperature difference, and you can see the differences there are much better for smaller members and for using the lower heat slags. Okay, so in conclusion, the adiabatic temperature rise is very dependent on the slag composition. And the aluminum and magnesium contents are important and indicators of the heat of hydration that you can expect out of the material. Your slag cement does react slower than your Portland cement, but can produce higher overall temperature rises after 7 days. But that doesn't necessarily mean that it's going to give you problems. You have to look at the rate of the hydration and your member size to see how that's going to impact it.